Stanford University.
Okay, we're entering today into the world of quantum field theory. Quantum field theory is, of course, the description of nature as we know it, with the exception of gravity. And so practically everything that we know, with the exception of gravity, in principle, we think is explainable if only we had the computational power to be able to solve quantum field theories with the accuracy that would be appropriate. Now, the problem is, of course, that problems tend to be much too complicated to solve, except for some very special problems. You can understand the hydrogen atom, but by the time you get to the boron atom, they're too complicated and so forth. And certainly studying human beings is well beyond the capacity of any quantum field theorist that I know. But nevertheless, apart from gravity, quantum field theory seems to be all there is. And we're going to enter into the study of it today in a very, very, very elementary way. We're going to study today the idea of what is called second quantization. But before we do, and second quantization is about quantum fields, but we'll come to it, I want to review something first and maybe generalize that something a little bit. The thing that I want to study or to remind you of or go through with you is, again, the harmonic oscillator. But a new aspect of the harmonic oscillator, a couple of new aspects of the harmonic oscillator, just so that we have it in front of us, because the harmonic oscillator is the central ingredient, the central mathematical structure that goes into quantum field theory. So we need to understand it, make sure we understand it well. But we're not going to worry about springs and systems oscillating. When I speak about the harmonic oscillator, I'm really speaking about the algebra of those little operators A plus and A minus, and the product of A plus times A minus, which is what? Do you remember? What is it? It's the number operator. It's the number of the excitation. So I'll remind you now. We'll go through it a little bit, and I'll tell you one or two facts that I may not have told you about. What I'm particularly, all right, so let's just write down the rules for a single harmonic, for a harmonic oscillator. There are A pluses. They act on states to elevate them up to the next level. There are A minuses, which take you down. At the bottom level, the ground state, A minus gives you nothing. It just annihilates the state. All right, so A minus is the lowering operator, and A plus is the raising operator. We're going to learn to call them creation operators and annihilation operators. What is it that they create and annihilate? As we'll see, particles. But let's just use the same conventions that we've used up till now. And there is also A plus times A minus. That was the thing, if you remember, that went into the Hamiltonian. If you remember, the Hamiltonian was just basically A plus A minus. What was it? A plus is x plus I omega p divided by some square root of 2 omega. A minus is the same sort of thing with a minus sign in there. And if you multiply them together, you get things with x squared plus, do I have that right? P plus, no, I have it wrong. That's p plus omega x. And if you multiply the two of them together, you get p squared plus omega squared x squared plus this extra little term that was the ground state energy. And so that went into the Hamiltonian, A plus times A minus, and we called it the number operator. It was the thing whose eigenvalues, whose observable values, were the integer level spacing, or the integer levels of the harmonic oscillator. So I believe we called this capital N, if I remember. And its eigenvalues we called little n, the observable values of it. One more thing, the commutation relations of A plus and A minus. That's what made, A plus and A minus are Hermitian conjugates of each other. That's an important mathematical fact. But the other mathematical fact is that the commutator of A minus with A plus is equal to 1. That's what made everything work. That's what we used to find the properties of what happens when we act with A plus and A minus. We used those commutation relations. That was basically it. That's all that went into the harmonic oscillator. Now, I'm going to suppose I have many harmonic oscillators. You could just think of them as a collection of springs, or you could think of them as the various oscillations of a violin string, or whatever, for whatever reason, there happen to be many independent systems that are undergoing oscillation, or that can undergo oscillations, possibly with different frequencies. Where does the frequency come into all of this? The frequency, well, first of all, it comes in here, but by the time we get to that point over there, the place where the frequency came in was just the fact that the energy is equal h bar times the frequency times this n here. There's also plus a half, or I'm going to leave out the half, the ground state. It's not important for us. All right, so that's where the frequency came in. It came in just as telling us what the energy for each increase of the number operator was. The frequency, together with h bar, determine each time we go up a level how much energy it cost to jump the oscillator up one level, or how much energy we might get back in some other form if the oscillator jumps down. If it jumps up for some reason, that's how much energy we have to pay, h bar omega. If it jumps down, that's how much energy we get. And as I said, that's the single harmonic oscillator. But now if we have many harmonic oscillators, we can label them. We could label them with an index. And I'll use the index I, but I does not stand for the square root of -1. It's just a label which goes over all the possible oscillators that I'm interested in. There may be a finite number. There may be an infinite number. In the examples that we'll be interested in, there are an infinite number. All right, so now we get to label the oscillators. Just by putting in, well, okay, we have to be a little careful over here. Each oscillator, think of it as an independent system, as a system which is just an independent degree of freedom. And when you have independent degrees of freedom, the operators for one subsystem commute with the operators for the other for any other subsystem. That's a rule. We went through it 2 years ago or a year ago, whenever it was. The operators describing system A and the operators for describing system B, if A and B are truly independent systems, they commute with each other. Why? Because to not commute would tell you that you cannot measure them independently. If you can't measure them independently, they're not independent systems. So presumably if you had two springs, you could take one off way over there and the other one way off over there, and there's no reason why they should influence each other. They're operators, everything about them commutes. And so we can write the following, that let's write out all the commutation relations because they're important. Let's forget this for the moment. Let's first take the commutation relations of the lowering operators. I with J. The first oscillator with the 14th oscillator. Okay, well, first of all, if I is not equal to J, they're talking about different oscillators. If we're talking about different oscillators, they must commute. But if we're talking about the same oscillator, then the commutator should be exactly the same as it was for the single oscillator case, namely 1. So how do we write that? We write that by putting the Kronecker delta over here. All that means, zero. Annihilation operators all commute with each other. Even for a single oscillator, the annihilation operator commutes with itself because everything commutes with itself. Same thing for the creation operators, or the raising operators. But now, here's what I wanted to say a moment ago. If I take the annihilation operator and take its commutator with a creation operator, then if I is not J, we're talking about two different oscillators. They don't know about each other, they don't talk to each other, or at least they may talk to each other, but they are independent of each other, and the commutator must be 0. On the other hand, if it's the same oscillator that we're talking about, then the commutator must be 1. So this is equal to delta ij. This is the algebra of the operators of many harmonic oscillators. You need to know that. And one more thing, what's the total energy? The total energy is just the sum of the energy of all the oscillators. So let's write that. The total energy, which we can take to be the Hamiltonian, is the sum over all I, all the oscillators, the first oscillator, the second oscillator, of omega. I'll include the h bar for the moment. I'll probably forget about it before the night is over. Omega, but which omega? Each oscillator may have a different frequency. So each oscillator, the contribution of the ith oscillator is proportional to the frequency of the ith oscillator times n sub I. We're going to give a name to n sub I now. We're going to call n, or n sub I, but n, we're going to call them occupation numbers. Not occupation like what's your occupation, but occupation in the sense of you are sitting there occupying some space. Okay? All right, these are the occupation numbers. It's just a name for the moment. What is it that's doing the occupying? Well, we'll find out. But this says that each oscillator has an energy proportional to its occupation number times omega, times its frequency, with the h bar being there. There is the extra half of ground state energy. I want to ignore it. It's of no interest. It plays no role. It's just an additive constant. Additive constants in energy don't make any difference. Okay, that's the whole theory, if you like. Well, not quite. Not quite. Now, how do we label states if we have many oscillators? If we have one oscillator, we can label a complete basis of states just by the level or the occupation number of the oscillator. Remember, we have all these states. N equals 0, which is the ground state, which we sometimes just call O. N equals 1, which we call 1. N equals 2, and so forth and so on. We label the states by the occupation number. That's a state. What if we have many oscillators? And I now imagine that I lay them out. There are many oscillators. Here's the first one over here, second one over here, third one over here, fourth one over here. I equals 1, I equals 2, and so forth. Okay. Then, in order to specify a state, I have to specify the occupation number, or one way of specifying a complete basis of states. One way of specifying a basis of states is to label, or is to write down the occupation number of each oscillator. How many quanta, or how many units of energy are there, so to speak, in the first oscillator. I'm going to call the first oscillator N1. N1, N2, N3. If there's a finite number of oscillators, it terminates. If there's an infinite number, it doesn't. Do you know any situations where, at least mathematically, there's an infinite number of oscillators? What's that?
The continuum?
Well, an example would be a very idealized mathematical violin string. A violin string has any number of harmonics. Every one can oscillate with a different frequency. That's a mathematically idealized. Of course, the real violin string is made out of atoms, and there aren't really that many possibilities, but a violin string would be a mathematically idealized violin string would have an infinite number of oscillators, but of course the very, very high N, the very high I, would correspond to extremely rapid frequencies, and really because of the atomic structure of the violin string, it really doesn't have that many oscillators. But that's an example mathematically of infinitely many. And we're going to be interested in that case. Okay, let's talk about, let's come over to another blackboard over here. We're going to, a little more oscillation, a little more oscillator mathematics. I told you originally that if you act with the creation operator, or the, I'm going to call it, I'll slip into calling it the creation operator. With the creation operator, you increase n by 1 unit. Well, that's not quite right. Not if we normalize the states in the usual way. The usual way to normalize a family of states, they're orthogonal to each other for different n. Why are they orthogonal to each other? Because they have a different, observably different number of n. So states with different values of an eigenvalue are orthogonal. So the usual normalization would be that the inner product of n with m is delta nm, or in other words, each state nn is equal to 1, nm is equal to 0. For n not equal to m, they're orthogonal. For n equal to n, we normally would take them to be normalized states. That's standard quantum mechanical notation, procedure. With that notation, in other words, each one of these states is of unit length. Each one of these states is of unit length, but with that notation, a plus on n does not give n plus 1. It gives a numerical coefficient in front, and the numerical coefficient is the square root of n plus 1. Let me prove that for you. Let's see if we can prove it. We can do it over here. Okay, let's not put the answer in. Let's just call this some numerical coefficient, and we don't know what it is yet. We don't know what it is yet. It's some Cn, and we're going to try to figure out what it is. What's our tool? Our tool is the commutation relations for the oscillators. It's a single oscillator now, not multiple oscillators. Okay. Let's write, this is a ket vector equation. Let's write the corresponding bra vector equation. When you go from a ket vector equation to a bra vector equation, what do you do with the operators? The kets go to bras. What about the operators? Hermitian conjugate. Hermitian conjugate. Hermitian conjugate. All right, the Hermitian conjugate of A plus is A minus. So another way to write the same fact is the Hermitian conjugate on the bra vector n is equal to Cn. I'm assuming that Cn is real. We can do the complex case. It doesn't matter. It's okay to think of Cn as real. It doesn't matter. But let's let it be real. If it wasn't real, then we would want to complex conjugate it. But we can choose it to be real, and then n plus 1. That's the exact same equation, except kets go to bras, operators go to their Hermitian conjugate, and numbers go to their complex conjugate, but I'm taking C to be equal to a real number. Okay, now here's what we're going to do. We're going to put this equation next to, we're going to take the inner product of this equation, with the bottom one with the top one. Let's write it out. N, A minus, A plus, N. That's what happens if you take the inner product of the left side here with the right side here. And that's going to equal Cn squared times the inner product of this vector with this vector. But what's the inner product of this with this? 1. 1. Every one of these vectors is normalized to 1, so it's just 1. So now we have a tool to figure out what Cn is. All right, all we have to do is juggle the A pluses and A minuses in a clever way. What do we want to do? I think I erased an equation over here. I should have written, yeah. Let's write down the guiding equation over here, or over here. N on the nth state is equal to little n on the nth state. Why is that true? Come on. Definition of being an eigenvector. Little n is the eigenvector of big N. Big N acts on the eigenstate with eigenvalue n to give little n. That's the definition of an eigenvector.
Question?
Yes?
I don't see why the inner product of n plus 1 with n plus 1 is 1.
Because I've used the rule.
But we haven't normalized them yet.
No. Now I've assumed they're normalized. I'm assuming now that the n vectors are normalized. And having...
Okay, go ahead.
No, I have put the ambiguity into the C's.
Right.
I may assume that they're normalized and then seek to... Got it?
All right.
Right.
So, yeah. Okay.
Yeah. Okay, good. All right, so big N is nothing but A plus A minus. So let's put that here. A plus A minus that's almost what I have here. A plus, I don't have A plus A minus, I have A minus A plus. But what I know is what A plus A minus does. What can I do? What's that operation? Commute. Commute. And here is our commutator. The commutator is 1. So what that says is that this same thing is equal to n A plus A minus plus 1. That's the commutator term, n. Okay, now I'm in good shape because I know what A plus A minus does when it acts on n. It just multiplies by little n. So all of this just gives me n plus 1 times the inner product of n with itself, which is what? 1. So there we have it. Cn squared is equal to n plus 1, and therefore Cn is the square root of n plus 1. We now know what the creation operator does in all of its glory. It increases the occupation number by 1, and it multiplies by the number square root of n plus 1. We can get rid of the rest of this. We don't need it anymore. Next, what about A minus on n? Well, you go through essentially the same little game. You can do it yourself. It doesn't take, it's not very hard. This time you don't even have to do any commutator. They'll wind up in the right order, and what you'll find out is that this is equal to the square root of n times n minus 1. In other words, it takes you down a level but multiplies by the square root of n. Notice that this one, yeah, okay, that's what you find. Once you know this formula here, you don't have to worry about the fact of what happens when A minus hits the bottom level. When A minus hits the bottom level is n equals 0, you get 0. So this equation as it stands now encodes the fact that the lowering operator annihilates or kills or gives 0 when it acts on the ground state at just this square root of n here. So this is more oscillator stuff that I assume that Dirac was responsible for. And now we know, I think, everything we need to know about harmonic oscillators, at least for the moment. And that was just a mathematical interlude, if you like, so that we'd have it in front of us when we need it. Let's put it up on top. Any questions about harmonic oscillators or multiple harmonic oscillators? Oh, one thing. What happens, here's a particular vector or a particular state which has a certain set of occupation numbers. Let's hit it with a creation operator for the ith oscillator. We're going to the ith oscillator and we're applying 1 unit of creation to it, or 1 unit of elevation. What does it do? Well, it goes over to the ith slot. If this were 3, if I was 3, it would go over to this slot, and it increases the occupation number by 1 unit, but only for the particular I that we wrote down here. So if we go to the 7th oscillator and we apply the creation operator, it increases the 7th oscillator level. It does not increase the 6th one. It doesn't increase the 5th one. You know, if there's an oscillator over there, it's over there. It's not to be confused with anybody else. And so what this does is it leaves all the other ones alone. Let's say I is out here somewheres, and 1 and 2, dot, 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 until we get up to the ith place. And then it gives us ni plus 1, and then beyond that, nothing. But this is not quite right. This is not quite right because it fails to take into account the square root of n plus 1. So what we actually have to write, what am I writing? I'm writing nonsense. Ni equals n1 dot 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 ni plus 1 dot dot dot. But we have to put in a square root of ni plus 1. So in other words, it works exactly the same as a single oscillator, with all the other ones just being bystanders, which play no role when you hit it with the ith oscillator. If you hit it with the jth oscillator, some other occupation number would get increased. Likewise for the lowering operators or the annihilation operators, same kind of understanding. So as I said, that's what we need to know about oscillators. Now we're going to come to quantum fields, real, genuine quantum fields, but in a very simple context. Non-relativistic quantum mechanics, ordinary quantum mechanics. Not relativity yet. We're not doing special relativity, just ordinary quantum mechanics. In ordinary quantum mechanics, there's some kind of funny connection between particles and fields. Particles are described by wave functions. Wave functions are functions of position. They sort of look like fields. What are fields? Fields are things, degrees of freedom, which depend on position and on time in particular. But let's just say position for the moment. Let's freeze time. Fields are functions of position. The wave function of a particle is a function of position. And so you might think that's all there is to it. That's the connection between particles and fields. But it's not. It's not. Or at least it's only a very tiny part of it. And in fact, not the real idea. It's right up here. Psi of x. Psi of x is the wave function of one particle where x is the position of that particle. X could stand for x, y, and z, of course. It doesn't necessarily stand for just x. But psi is a function of x. But what is it? It's not an observable quantity. It's the state vector. It's the state vector in the position representation. It's not an observable. You don't do experiments to measure the wave function of a particle. You do experiments to measure the position of a particle, or the momentum of a particle, or the angular momentum of a particle, but not the state of a particle. You don't measure, that's not a measurable thing. It's a thing which tells you a great deal about the probabilities of various measurements, but it itself is not an observable. So that's the first thing, not an observable. Next fact. If we have several particles, then psi is not a function of one position. It's a function of all the positions. I want to exaggerate a notation a little bit. I want to make this a small psi, a lowercase psi. And it's a wave function. If I have two particles, let's call them x and y, again, not the x coordinate and the y coordinate of space, but just the coordinates of two particles, then the wave function is a function of two positions. All right? Function of several positions. In fact, it's a function of the position of all particles. Third fact, what was the third fact? The third fact is given a wave function which may depend on x1 through some number, whatever, x15, 15 particles. It's the description of a fixed number of particles. We describe 15 particles with a 15-particle wave function. Fixed number of particles. That is not the idea of a quantum field. By contrast, now, I'll tell you by contrast what a quantum field is, and in many respects it's everything that this is not, although we tend to use the same notation for it and it's closely related. Okay, first of all, a quantum field, these are wave functions, and they represent state vectors. Capital Psi is different. Number one, it's an observable. It's a thing you can measure. Let's just think for a moment. What is a quantum field really going to be in when we get to the real thing, more complicated, serious quantum field theory? It's going to be things like the electromagnetic field. It's going to be the quantum mechanical electromagnetic field. The electromagnetic field is most certainly an observable. We observe it. And so, first of all, whatever psi is, it is an observable. Number two, psi is a function of only one coordinate. Oh, incidentally, the fact that it's an observable means that it's an operator. It means that it's an operator in the space of states. It's not itself a state. It is a operator. That must be if it's going to be an observable. Number two, it's a function of only one coordinate of one position. Function of one free vector, so to speak. And finally, it describes systems of any number of particles, any number of particles. In other words, it's capable of describing systems where particle numbers can change even. Where particle numbers can change. How can particle numbers change? Well, if we were thinking about the electromagnetic field and we remember that electromagnetic field is photons, every time electromagnetic field is radiated, it changes the number of photons. So whatever psi is, it's a description, it's an observable, it's an operator, it's a function of one position, and it represents the quantum mechanics of any number of particles, not a fixed number of particles. That's number one. I don't want to go too fast because this is tricky stuff. Yeah.
So when you say function of one position, you mean the position x, where x can vary?
X can vary. Yes, x can vary, but it's a function of only one x. Oh boy. It's a function of only one x, but that doesn't mean it's a function of x when x is 5. It means it's a function of x. X can be anything, but it's not a function of x1, x2, and x3.
What happened to y, though?
I keep telling you, why do... I mean, why...
Why is it not y? Yeah.
It's just a function of one coordinate. One coordinate in real world means 3 coordinates. It means x, y, and z.
But that's not what that y is. That's
No, that's not what that y is. That y, 2 particles. One is named x, the other is named y.
Right.
Why? Because who's on first, that's why.
So that's really just a special case of an x line. You've got 2 particles at psi x, y.
Yeah.
You got 15 particles at psi x,
Yeah,
1,
yeah,
x, 15.
that's right.
Okay.
Right. Y is just x2. X is x1. Right. And 1 and 2 label 2 different particles. Right.
How do these transform to each other? How do you explain one in terms of the other?
We're going to do that. That's the whole point. I laid out for you the big contrast, and now we want to know what's the connection between them. And it's going to take a little while, but it's not...
Different kind of particles?
No, same kind of particles. Same kind of particles. And in particular, bosons. We'll come to fermions later. We'll come to fermions later. Yes, this is the theory of bosons. Everything we're doing tonight will be bosons.
Excuse me. I had a question back on the left-hand board about the...
What's that, the what?
A question on the left-hand board about the harmonic oscillators. Is the assumption about the independence of the different operators exact or approximately correct?
Exact.
Okay. So, for example, I would not be used to index the electrons in an atom.
Say it again.
I would not be used
I?
to... Yeah, the subscript. That wouldn't be used to index...
I could be labeling the states of an electron in an atom. Now, you got to be careful. If the electrons are interacting, then it's more complicated. But if you just had non-interacting electrons in an atom, I would be labeling the states of the atom. Okay, but we're going to come to that. Yeah, let's come to it right now. Let's go back to single particle quantum mechanics. This is the theory of many particles. Well, it could be the theory of no particles, it could be the theory of one particle, it could be the theory of two particles, variable number of particles. Let's go back to the theory of just one particle. Okay. And for simplicity, I'm going to take a particular example, a particle in a box. The potential energy is such that the particle can't get out of the box just one direction of space, although nothing I'm saying is going to depend on that.
This is a boson in the box?
A boson. For the moment, it doesn't matter. If there's only one of them, it doesn't matter.
Okay.
If there's one of them, there's no question of whether there's an exclusion principle or not. Right? So one of them doesn't matter. Let's think about the energy eigenstates of a particle in a box. They're wave functions. For example, the lowest energy wave function will be the smoothest wave function that satisfies the Schrodinger equation. And it'll typically look something like that. It'll be a sine function that just barely fits in the box, that fits in the box from one end to the other. And that's a wave function. It's a wave function in the sense of this one over here. Let's give it a name. Let's call it psi 1 of x. This should be little psi. Just make sure it's little psi. It's just a wave function of a one-particle system in a box. Psi 1 of x. What does the 1 represent? Just that it's the first energy level, the lowest energy level. What about the next energy level? The next energy level is some other wave function. And as you go up in energy, the wave functions tend to be more variable. The next one would have a node, like that. We can call that psi 2 of x. I'm using a funny notation. The index here is not the number of nodes. It's one more than the number of nodes in the box. So the next one would be psi 2 of x. Would have a higher energy. And so forth and so on. Now the 1s and the 2s here do not represent, go down the line, psi I of x. Now this I will be the same as this I eventually. But at the moment, they're two different things. In this case, it's labeling oscillators. In this case, it's labeling state vectors of one particle in a box, just one particle. Each one has an energy. I won't write down what the energy is, other than to remind you that each of these wave functions does have an energy. Okay, everybody all right with that? One particle wave functions? Now, let's imagine now that we have many particles. We have many particles of an undetermined number, but some number of them in state 1, some number of particles in the box occupying state 1, some number of particles occupying state 2, some number of particles occupying state 3, and so forth. That is a pretty good description of a wide class, or a basis of states, in fact. If I know that is a basis of states, saying how many particles occupy each energy level. Okay, so let's write that down now. Here's a family of states. Number of particles in state 1, number of particles in state 2, number of particles in state 3. Oh boy, déjà vu. Where is, here it is over here. Absolutely identical to the way I labeled the states of a multiple harmonic oscillator system. Now, of course, there are infinitely many possible states in here of arbitrary wavelength, arbitrarily small wavelength, and that's the reason why we need to study any number of oscillators up to infinity. Okay? So here is a parallel between, you wouldn't want to do this you couldn't do this for fermions. For fermions, you can either have no particle with a particular state or one particle, never two. Okay? Can't put two. So in writing down the idea that you can have any number of particles in the first state, any number in the second state, any number in the third state, we're assuming to begin with that we're talking about bosons. Okay? But notice, there's complete parallel here. Because there's a complete parallel, it means we can invent, this is an invention out of the head, operators which do exactly the same thing as the creation and annihilation operators do. Now they literally create particles. For example, a plus 1 on n1 dot 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 gives me square root of n plus 1 n1 plus 1 times n1 plus 1, n2, n3, and so forth. It increases the number of particles in the first state. Whatever it was, it adds 1 and multiplies by the standard square root. Why does it multiply by the standard square root? That's a definition. But it's a definition which is very cleverly chosen, among other things, so that we can use all the apparatus that we have about oscillators, which is very helpful, as we'll see. Likewise with the annihilation operator. Now I'll call them creation and annihilation operators. They create and annihilate or remove particles from the system. Okay, that's the basic idea of creation and annihilation operators.
Question.
Yeah.
On your top line there, N1, N2, N3, I thought N1 and N2 were the quantum states.
1, 2, and 3 are the quantum states. N1, N2, and N3 are the number of particles in that state. 1, 2, and 3 are 1, 2, and 3 up to I, and past. Okay, so this is tricky. There's a lot of notation, but the notation it's not hard, it's just a bit to remember. So I'm going slow for that reason and repeating myself.
Question, please. What's the physical meaning in this environment of that square root?
A plus A minus on n is equal to n times n, right? Well, A plus is an awful lot like A minus, so it better be that A plus and A minus are somehow square roots of n, but we can do better than that. Let's see, how can we do better than that? Let's use the commutation relations. No. Okay. Let's suppose we didn't know this. Let's suppose we didn't know this, but we did know about the square roots of n. Okay, let's suppose we knew about the square roots of n. Okay? Let's use our commutation relations to write this as A minus A plus on n minus 1, I think. Yes? A minus A plus is equal to A plus A minus Plus 1. Plus 1, right? Hmm? 1 minus?
1 minus the other.
Well, let's see. A plus A minus A plus minus A plus A minus is equal to 1. So, plus 1. No,
You were right.
I was right.
A plus A minus over to the other side. You get a plus, and then take the 1 over and you get a minus 1. So
Right. I had it right. If it doesn't work out, we'll change it. Okay. Now, what does A plus on n do? According to assumption, it gives you square root of n plus 1 times n plus 1. Okay, that's over here. But we still have to multiply by A minus. And then we have another minus n. That's what we have here, right? Okay, this is just a number, square root of n plus 1. Let's put it over here, square root of n plus 1. What does A minus do when it acts on square root of n plus 1? Oh, sorry, on n plus 1. No, I think, yeah, it gives us n, but what's the numerical number? Square root of n plus 1, right? So we get 2 square roots of n plus 1, which gives what? N plus 1 times n minus 1 times n, which is just good old n times n. In other words, those square roots of n are there to ensure that this vector is really an eigenvector of A plus A minus. And roughly speaking, very roughly, A plus and A minus are of the same order of magnitude. One is P plus IX, the other is P minus IX. Same order of magnitude. And since altogether they add up or they multiply together to give you n, each one is roughly the square root of n.
question?
Yeah.
So,
Okay.
you just sort of define A plus and A minus. You haven't really defined them, but you define sort of various properties that they have, like the commutation property.
Yeah.
So, but we don't have a definition yet of it, other than kind of its behavior.
We're making it up.
Okay.
We're defining. We're not making up randomly, but we're defining things. And then we're going to see how they work.
Forgive me. My question was, I understand when you apply A plus, you create a particle.
Mm-hmm.
That's a very tangible thing. I didn't understand what does its square root do in a tangible sense. That's what
Nothing.
my question.
That's all. Well,
Or maybe nothing.
sometimes
that's fine.
mathematics is just mathematics. I mean,
Okay.
sometimes.
It's like you, for ordinary quantum mechanics, you have to normalize the wave function. If you only have one particle, it's the same thing here.
Okay. All right.
Right.
Why doesn't particle disappear? Why doesn't it become a different state?
What? Don't-
When you do A minus, why does it disappear? Why doesn't it become a different
That's
state?
the definition of A minus. You can't ask why about a definition. I define A minus so that it decreases the number of particles.
Okay.
Definition. In mathematics, we make definitions, and then we find the consequences of them.
So,
The question is, why is it a useful definition? Well, it's a useful definition because we want to explore systems of various numbers of particles. In fact, we want to explore systems where the number of particles can change. For example, we might radiate a photon. How would we go about mathematically indicating that we created a photon? We take the state and we hit it with a photon creation operator. Or a photon might be absorbed. An atom might absorb a photon. How do we write the fact, or how do we express the fact that the photon has disappeared? We express it by saying an annihilation operator has acted. So the purpose of all of this is not only to be able to study systems of arbitrary number of particles, but even to be able to study systems of variable number of particles. Okay.
Another question?
Mm-hmm.
So, here's what I think you're doing. What you're doing is you're defining these operators, how they act on eigenvectors.
Yeah,
And since eigenvectors form a basis,
yeah,
that tells us how they act on all vectors. Okay, I got that part.
right on.
Okay, now we've got this definition of A plus and A minus. We haven't shown, but one assumes that one can show that you have the commutation relationships that you've got up there.
Yeah, with
Okay.
these definitions, it will follow that these operators have the same commutation there. Right. In other words, the system of a variable number of particles here can be represented just as a system of harmonic oscillators, and an oscillator for each state. For each single particle state, for each single particle wave function, an oscillator and the occupation number of that oscillator is the number of particles that are occupying that particular state. So the terminology is well chosen. Occupation, now we know what it means. It's not you occupying your seat. It's a particle occupying a state, and a boson in particular. These are creation and annihilation operators for particles. How would you label, what's the vacuum in this language? The vacuum, well, first of all, it's the state which is annihilated by all of the annihilation operators. It's the state which, when you try to lower any occupation number, there's nothing there, nothing to lower, so the state becomes 0. But the vacuum is simply the state with 0 occupation number in every state. It has the property that all the occupation numbers are 0, and it has the property that any one of the A minuses gives 0 when it acts.
So the ground state is unoccupied as well.
The ground state is unoccupied. Right.
But
Now,
if it was occupied, you still couldn't lower it.
if it were occupied, you can lower it.
The ground state?
No, the ground state is not occupied. You can't occupy. That didn't make sense. The ground state and the vacuum are the same thing. Sorry. Right. While we're at it, let's write an expression, which we can now do, for the energy of the system. In order to write an expression for the energy of the system, we need to know the energy of each one of these wave functions. Each wave function has associated with it an energy eigenvalue. What shall we call them? The energies. We could call them E, couldn't we? I'm going to call them omega, or actually h bar omega. But let's just call the energy level of the ith. Let's kill h bar, forget h bar because I've already forgotten it. And just say the energy of a particle in the first state would be omega 1. The energy of a particle in the second state would be omega 2, and so forth. The energy of a particle in the ith state would be omega I. Let's write an expression in terms of creation and annihilation operators for the energy of the whole system. This is easy. The energy of the whole system is, first of all, the energy of all of the particles in the first state. So that's the number of particles in the first state, N1, times the energy that's associated with particle in the first state, omega 1, plus the number of particles in the second state times omega 2, plus and so forth and so on. So it's the sum of n sub I omega sub I. Now, that's a true statement, but I want to write it as an operator statement. These n's are eigenvalues, but they're eigenvalues of the number operator. So we can really write this in operator form by saying it's the sum over all the states, single particle states, of omega I times the occupation number of the ith state. And what is the occupation number of the ith state? A dagger I AI. Notice that each one of these is just basically the oscillator formula. This is just the oscillator formula. There would be an H bar in here. Put an H bar if you like. This is just the oscillator formula, but now it's summed over all the possible states here. And you can think of it two ways. You can think of it somehow the system of particles is equivalent to oscillators, and those are just the oscillator energies. Or you can say it's just the sum of the energy of all the particles. The number of particles in the first mode, first state, times the energy of the first state, plus the second state times the energy of the second state, and so forth, and it comes out to the same thing. Yeah?
Question, what is AI?
AI? A minus I, sorry.
Okay.
Good.
So A, what is A dagger?
Creation. Oh, sorry.
A plus?
Yeah,
Okay. got
good.
it. Okay, thanks.
In many contexts, once you go to quantum field theory, which is what we're doing now, A plus just becomes A dagger, and A minus just becomes A. Well, I'll try to stick with the same notation. I don't want to change notations now. Okay, so let's just think for a minute. What are we doing? We're inventing some kind of object which is a bunch of oscillators. On the other hand, the violin string is a bunch of oscillators. The violin string is a field. If you look at radiation in a cavity, radiation bouncing between mirrors, it's a bunch of oscillators. People speak, I mean, this goes back from long before quantum mechanics, speak about radiation as a collection of oscillators. Radiation oscillators, long before quantum mechanics. And so we're beginning to build up, from thinking about ordinary particles, we're beginning to build up an idea of collections of particles as harmonic oscillators, and soon enough we're going to see the connection with fields. Okay, if there are no more questions, maybe we'll take a 5-minute break because I need to stop for a few minutes. And organize your thoughts, and we'll field a few questions before we go on.
So that's Hamiltonian, right?
Is what?
That's the Hamiltonian, that's a Hamiltonian?
That is the Hamiltonian. That is the Hamiltonian. We're going to find other very elegant ways to write it. But that is the Hamiltonian, right. Okay. Yeah. Okay. I want to be able to remember where I left off. Okay. Good. Pat, what do you do with them? You put them on.
I'm not sure what he's doing.
I don't know what those are either.
He's already got the website up and running.
Yeah. I assume he puts them up. I don't know.
Well, I don't know if he puts it up directly. I was doing it many years ago.
I thought that was the idea, but I don't remember. Yeah, okay. Ah. Take a nap.
So do those normalization factors apply to the harmonic oscillator too?
What's that?
Those normalization factors, square root of n plus 1,
Yeah,
they apply to the harmonic
Yeah.
oscillator? Seems like exactly the same method.
yeah, absolutely. What's that?
The energy levels aren't spaced evenly in the box.
No, that has nothing to do with it. No, the energy levels, no, it's not the energy levels of the single particles in the boxes which are evenly spaced. It's the energy levels of no particle, one particle, two particles, three particles, which are evenly spaced for each oscillator. Right.
But isn't it in the simple harmonic oscillator for a single particle, the energy levels are all evenly spaced apart?
Yes.
Okay.
Yeah. No. No, we're not talking about particles which are moving in a potential which is an oscillator. You could. You could think of a lot of particles in a potential of an oscillator. Then you would have two kinds of oscillators. The particles would be oscillators and the creation and annihilation operators would be oscillators. But now we're just talking about any collection of single particle states. Single particle states is just what you would have thought about where you're just thinking about one particle quantum mechanics. But now, since we can talk about any number of particles, we can generalize in this way. Okay. Okay, let's get back. Are there some questions? Because I don't want to go too fast. I know that there's a lot of little indices and little pieces and nuts and bolts here, which if we go fast, they'll slip out of your head, and they slip out of my head from time to time. And yes.
So there's a connection between that and Fourier decomposition.
Mm-hmm. For sure.
In
Yes.
Fourier decomposition, you're going to have arbitrary amplitudes to deal with.
The A's are the complex amplitudes of Fourier coefficients. Right. We'll come to that. Yes, it's deeply related with Fourier analysis, absolutely.
Are we assuming that all the particles have the same energy?
Same energy? No, 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 no. If they're in the first state, they have energy 1.
Right.
All the particles which are in the first state have the same energy. Yeah. All the particles in the second state have the same energy as each other, but not as the ones in the first state. So, you know.
But
right.
they interact with each other.
Well, okay, for the moment we're talking about particles that don't interact. For the moment we're talking about particles which simply don't interact with each other. That's the starting point. Later, we have to ask what kind of things do we have to do to get the particles to interact. What Giorgio was saying is that if particles really interacted with each other, the energies wouldn't really be additive. There wouldn't just be the energy of particle 1 plus the energy of particle 2. There would be the energy of particle 1 plus the energy of particle 2 plus any kind of potential energy between them, for example. So right, so that's correct. For the moment, we're talking about free particles. Free particles means particles which don't interact with each other. Okay, now we come. No other questions? Yes.
So in non-relativistic quantum field theory, there's still a half a boson in the ground state?
Yes, but it doesn't play. It doesn't do anything. It's just 0-point energy. And why doesn't 0-point energy? Why is it irrelevant for everything? Well, if you think, energy is Hamiltonian. What happens if you add a constant, a number, to a Hamiltonian? Well, a number commutes with everything. And if you remember, what the Hamiltonian does for you is it provides a method of getting equations of motion. The time dependence of something is related to the commutator of that thing with a Hamiltonian. Constants do nothing. They commute with everything. Another way of saying it is, in keeping track of energies, the only thing that really counts is energy differences. So you can throw away that ground state energy except for certain very special purposes that are not going to concern us right now. Okay, quantum fields. A field is a function of space. It's not a function of 2 points of space or 3 points of space, so it's not like the wave function of a many-particle system. It's a thing which only depends on one coordinate. It's also an operator. Why? Because it's an observable. You observe fields, you measure them. What was the third point about? Well, I don't remember. But it somehow has to do with your ability to change the number of particles. Okay, so what we're going to do is I'm going to give you the rule for the quantum field of this system of particles. And then we're going to explore how it works. If you ask me prematurely why that's the definition, well, it won't work. It won't work. The best thing to do, sometimes it's just best to follow the definition. And I promise you, we won't go too far before you'll start to see why it works and why it's interesting and why that's the definition. But it's better not to try to intuit out from the beginning why this is the particular definition. Rather get used to it and familiar with it, and in a short amount of time you'll understand why that's the thing to do. The definitions, the value of the definitions depends on their utility, all right, on what you can do with them. And I might say this to begin with. Quantum field theory, at least in the way we're thinking about it here, among other things, is a bookkeeping device. It's a bookkeeping device for keeping track of many particles, for keeping track of the quantum mechanics of particles which come and go, change their state, even disappear and reappear, whatever. It's a kind of bookkeeping device. Whenever you have operators like this, you're doing bookkeeping. It's a little more than that, because you can actually measure these fields. The things, when they go by you, you feel them, they have an effect on you. But for the moment, we can just think of it as bookkeeping. And whether a definition is a useful definition or not depends on what you try to do with it. And I can tell you, with quantum fields, you can do a lot. Yeah?
Could you take a minute or two to say just a little bit about the history of quantum field theory, when it was developed, who developed it?
Well, we go way, way back. We can start with the question of who invented field theory. All right? Who invented field theory? Anybody know who invented field theory? I suppose it was Faraday with the electric and magnetic field. So I think probably the idea can best be the original history started with, I think, with Faraday. Maxwell invented field equations. Faraday didn't have field equations, he just had a feel for the fields, and was able to visualize them. Maxwell wrote down, as far as I know, well, it's probably not true that he was the first one to write down a wave equation. There were wave equations, waves of water, waves of other things, but I think it can fairly be said that Maxwell wrote down the first modern version of field theory, but it was classical field theory. The need to quantize fields, or the need to do something involving h bar, goes back to Planck. Planck, well, it goes back before Planck. We have not talked, we will eventually talk about what is called the ultraviolet catastrophe. Won't talk about it now. But Planck realized that classical field theory would not be adequate for studying thermodynamics of radiation, introduced Planck's constant, and in the process basically said some things about harmonic oscillators which were more or less correct. He didn't realize that the radiation field itself was made out of oscillators, or photons, as we call quanta of the field. He was thinking about the oscillators in the walls of a cavity, namely the atoms, which he thought of and envisioned as literally oscillators, little oscillating charges. And his application of Planck's constant, and he didn't have his mathematics, but the idea that the energy levels were integer spaced, he wrongly thought that that had to do with the oscillators in the walls of the cavity. It was Einstein who first understood that the quantization of oscillations had to do with the electromagnetic field, with Maxwell's electromagnetic field. So, as with almost everything else, it was Einstein who had the first inklings of this. But then later, it was Heisenberg, Pauli, Dirac was the person who really put it together in the form we're talking about. And that was basically around 1929. Around 1929, a lot of these ideas first really surfaced. But you know, as usual, Einstein really did have all the ideas, and although he hadn't articulated them in exactly the modern form. After that, the whole history, but not for tonight, not for tonight. This notion of particles or variable number of particles as harmonic oscillators, that's a good question. Who was the first one? I'm guessing Dirac again, but I'm not sure that he was the first one to identify particle creation and annihilation as a form of harmonic oscillator mathematics. I would guess it was Dirac, probably around 1930.
What was the first major problem that they could solve that hadn't been solved before?
The first major problem was the problem of the ultraviolet catastrophe or basically why radiation was quantized. Einstein knew radiation was quantized. Okay, he knew that radiation came in photons, but he didn't have a mathematical way to think about it. The first major problem that was solved was a formal mathematical quantum mechanics that was consistent with the rest of quantum mechanics, that included the idea that radiation came in photons. That radiation came. So far, we have never even talked about what a photon is. We're getting close. We're getting close. A photon has something to do with the electromagnetic field, and it's a unit of energy. It's like these occupation numbers. Okay? The things which occupy the occupation numbers are quanta. If the particles we're talking about are the quanta of the electromagnetic field, they're called photons. So that's where we're going, we're really getting close to talking about what a photon is, or what a quantum of a field is. In fact, right now we're going to introduce the notion of a quantum field, the simplest version of it. I'm going to give it to you as a definition, and we're going to see what it does and how it works. Okay, so psi is a quantum field, and I'm going, again, because it's a quantum field, it's an operator. It's something you can measure. I'm going to call it capital psi. It's an operator, but it's an operator which depends on position. So it's not a single operator, it's an operator for each position. For each position, a separate operator. It acts on a space of states. The space of states, what is the space of states? The space of states, where is it? We erased it? Well, the space of states, n1, n2. Incidentally, this is called Fock space, F-O-K, F-O-C-K. Fock was a Russian physicist. I doubt very much that he was the first one to use this, but he wasn't. But it got named after him for the usual reasons that things get named after people, namely no reason. Okay, the quantum field psi of x. It's just a very short definition. It's equal to the sum over all of the single particle wave functions, sum over I, a contribution for each one of these states. So it's a sum over I. It contains psi I of x, the single particle wave function. These are things like sines and cosines of different wave number, of different wavelength. That's what goes there. And what multiplies it, the coefficients are the creation and annihilation operators. In this case, the annihilation operators, I. Now, somebody asked me if any of this has to do with Fourier analysis. If the psi's are if the psi's were momentum eigenstates, that means they're sines and cosines, then these operators A minus would resemble very closely the coefficients that occur in Fourier analysis. That is, they are the quantum version of the Fourier coefficients when you expand the thing in sines and cosines. Now, it might not be sines and cosines. It's whatever the orthonormal family of states, of single particle states is. That's it. That's the definition of a quantum field, the simplest example. What's that?
Left-hand side is an operator, right? Right-hand side, does it include the psi there?
These psi's are just numbers. Now, in fact, there's a separate number for each position. Psi of x are just just functions. So if I want to know what the quantum field is at x equals 0, I plug in x equals 0 here. If I want to know what it is at x equals the square root of pi, I put in the square root of pi here. So it's a whole set of it's a whole set of operators, one for each position in space. That's a lot of operators. One for each position in space. Why so rich? Why are there so many operators? The reason is because we're trying to study a system where there can be any number of particles. That's a lot of states. A lot of states, a lot of operators, just because the number of particles is totally unbounded in this idea. Okay, so there's an operator at each position. This x and this x are the same. The size are different. This is an operator. This is just a function of position. The operator is in here. That's where the operator is. Okay. There is the complex conjugate or the Hermitian conjugate is an operator. It's not a number, but it has a Hermitian conjugate. It's exactly the same thing, except that we put creation operators there and psi star here. These quantum fields are not Hermitian. They're not Hermitian because the creation and annihilation operators are not Hermitian, and so they're not really observables. But if you add psi and psi star, or psi dagger, or you subtract them, you can make Hermitian combinations out of them, and those really are things that you could observe in the laboratory, just because they're Hermitian operators. All right, now we're going to explore these. We're going to explore these objects. We're going to go slow. But the first thing I want to show you is what the action of psi is, psi of x, capital Psi of x, when it hits the vacuum. What does it do when you apply it to the vacuum? Let's take psi dagger. We'll take psi dagger. Incidentally, what does psi do when it hits the vacuum? It kills it. It annihilates it. Why? Because it's only got annihilation operators in it. Psi dagger, however, has creation operators. It creates a particle. Each term in here creates a particle. It doesn't create a lot of particles. It creates a superposition of particles, but one particle in a superposition of states. So let's see if we can figure out what it does when it hits the vacuum. Okay, so here's what we're going to do. Let's take single particle quantum mechanics, one particle quantum mechanics to begin with. In other words, forget all this fancy stuff with oscillators, just the good old quantum mechanics of a single particle. There's a complete set of states. The complete set of states are the position states. Let's see, how do I want to write this? Okay. States which are located where the particle is located at position x. They're a complete set of states. That means they're a complete basis of states, and that means that you can, if you sum over all positions or integrate over all positions, I'll keep it simple. I'll imagine summing over positions, but we may have to do an integral. If we sum over all positions, what do we get on the right-hand side? 1, the unit operator. That's a general rule for any basis of states. Okay, now, let's see, I just trying to remember which way I did this. Ah. That's a true statement, but it was what I actually wanted was a different statement. It is a true statement. But what I actually wanted was this statement. Sum over I. As usual, about this time at night, I start making mistakes. And I was just about to make a mistake, but I caught myself. What are these I's? Do you remember? They're the one particle states, the ones which look like this. Psi 1, Psi 2, Psi 3, Psi 4, and Psi 5, and so forth. They are a complete, they're the energy eigenstates. They are a complete set of states. If I take all the signs that can fit into here, for example, sine of x, sine of 2x, sine of 3x, sine of 4x, that's a complete set of states. Each one of these i's here is a state whose wave function is psi I. But the psi i's are a complete set of states, and so it follows that this expression here is just a unit operator. This is true for any complete basis of states. You go back to your quantum mechanics and you remember what this means. Now, that means there's a little bit of trickery, but there's nothing deep going on here. The sum of I, that's an operator. That's a unit operator. It's trivial. It's a unit operator. And what happens if I apply it to a state in which the particle is known to be at x? What do I get? I get a particle at x. I've done nothing. I've just rewritten the particle at position x. On the other hand, what is this object over here? Well, it's a coefficient, all right, but it's also a wave function. Do I have it? Yes, it's a wave function. It's the wave function of the state I, the inner product of a particle at x with the state vector I is just, is it psi or is it psi star? Anybody know? I know. Happens to be psi star. Happens to be psi star. So this can also be written as the sum over I, psi star of I of x times the state I. That's a particle located at point x. Now let me slow down here and get any question about this, because I'm sure this must be a little bit confusing. This is the unit operator. We apply it on a state located at x, and it gives us a state located at x. On the other hand, this inner product of a particle at x with the wave function psi, or the state vector psi, is just psi star of I. It's just a wave function. Okay? But what about this? What about the state here? That state is one particle with wave function psi I. I can write it another way. I can write it as follows. I is equal to A plus I on the vacuum. The vacuum has no particles in it. If I create a particle in the state I, then indeed I have a particle at I. I have a particle in the state I. So I can substitute for this, I can substitute A plus I on the vacuum.
It's not a power raised to a power?
No, one particle.
Okay.
One particle. This is one particle in the state I. That's all, just one particle. Okay. And it gives me a particle at position x. But wait a second. The thing that I wrote down here is exactly the quantum field psi dagger. So we can now write this in another form. We can write a particle at position x is psi dagger at position x on the vacuum. So now we know what psi dagger is. It's an operator which creates a particle at position x. If we have no particles and we want to create a particle, we want to change the number of particles by adding one at position x, then the way to do it is to apply psi dagger to the vacuum. Creates a particle at position x. What if we wanted to create another particle at position y? Well, it's not too hard to work out, but what do you expect? You expect just hit it with the field operator. We'll call this the field operator now, or the creation, the field operator. We just hit it with another psi dagger, but at position y. So whatever the state is, if you want to add a particle at a particular location, that's the job of the quantum field. It's a function of x, y. No, not y. Who? It's a function of x because it has to know where to put the particle. It's an operator that puts a particle at x. It's not the operator that puts the particle at y. So it must be itself a function of x. That's what, in a simple situation, the simple situation that we're working on now, that's the meaning of the quantum field. It creates a particle at position x. The creation and annihilation operators create particles in the energy eigenstates. You apply a dagger to the vacuum, and you get a particle not at position I, that doesn't mean anything, but in the wave function I, sines and cosines and so forth. That's the meaning of A+. On the other hand, when you combine them together into the quantum field creates a particle at position x. What do you think? Yeah, what do you think the annihilation or what do you think the other piece does? That removes a particle at x, if there's one there. What if there's none there? Then it annihilates the state. So psi dagger creates a particle at position x, whether or not there's one there. Psi annihilates a particle at x or gives 0 if there's no particle there.
Question, please. Where is the information? What kind of particle to be created buried in? It should be in the little A+, but...
First of all, we're talking about bosons. If you get fermions, you don't do them this way.
Which boson?
Right. There's a separate quantum field for each species of boson. So what kind of bosons are there in the world? There's photons, there's gravitons, there are Higgs bosons, there are gluons. For each species of boson, there is a separate quantum field that creates that kind of particle in this manner. Right.
So the particle is being created with a delta function probability distribution.
By psi of x. That's right. Right. That's exactly right. So, right.
Excuse me. So if there's no particle at position x, then psi of x does nothing?
No, it gives 0.
What does give 0 mean?
The same thing that when an annihilation operator hits a state with no particle in it, or when the annihilation operator hits the ground state, gives 0.
So it's doing nothing?
No, it's giving 0.
What is, thinking of it in terms of particles and positions, if there's nothing at that position, what does it mean to give 0 to a position, I guess?
You started with a vacuum. The vacuum is not 0. The vacuum is a state. It's a normalized state whose length is 1. It's a good state. There's nothing wrong with it. It's there. But it has properties. The properties are those of empty space. When an annihilation operator hits it, it literally gives 0, the 0 vector, the vector of 0 length.
Now I don't understand what that is. How can you have a 0?
0 is the unique and only vector that if you add it to any other vector, you get the same one back. It's a vector in a vector space. Go back to vector spaces. Vector spaces have in them 0 vectors. 0 vectors are vectors of 0 length. It's not interesting. It doesn't have any properties. It's just
It
doesn't describe anything.
It doesn't describe physically the thing itself.
Doesn't describe physically anything. It's just.
If you add vacuum, you get something else.
Hmm?
So if you add the 0 state,
To the
you
vacuum?
get the same thing. What if you add the vacuum state?
You certainly don't get the. If you add the vacuum, let's say to a 1 particle state, then you get a state which has, let's say you add it with equal coefficients, just to be simple. Then you get a state that has a probability of a half of having a particle and a probability of half not having a particle. You see, if you add the 0 state, not the vacuum, to a 1 particle state, you just get the 1 particle state. If you add the vacuum to the one particle state, you get something that has a statistical probability of, let's say, a half to have a particle, and a statistical probability to not have a particle. Zero cannot be normalized. It is definitely not normalized. It's of zero length. The one thing that you can't normalize is a vector of zero length. Right. The vacuum is not a vector of zero length. For a little bit of time, people generally get confused by the notation. This looks like it's zero, but it's not zero. It's just a name. The zero here does not mean that it's a vector of zero length. It does not mean that if you add it to another vector, you get back the same vector. It's just the name of the vector, and it represents a perfectly good physical state. It happens to be a state with no particles in it, but it's a state. It's empty space, but it's a state.
So we could have put a half in there instead.
You could have called it, right, you know, you could have called it George Bush or whatever you want to call it. It doesn't matter.
Once you've annihilated
You know?
once you've annihilated the vacuum, you can't create anything in it again, right?
We won't talk about annihilation and George Bush in this thing. Yeah. That's right. Once you've annihilated it, you can't put anything back. Right. It's just zero. It's literally zero. Right. Right. Any operator that acts on the zero vector just gives back the zero vector. Doesn't give anything interesting. Right. You know, it's like 1 minus 1 is 0. Take any vector and subtract it from the same vector, and you get 0. If you add 0 to any number, you get the same number. Add the vector 0 to, you know, here. Here's the 0 vector right there. It has no length. The vacuum, on the other hand, has a length of 1 as a vector in the vector space, normalized. Not easy. Not easy. Not easy, but you get used to it.
On the left board, the lower sum,
Yeah.
does the order of those operators?
No. No. This is an operator. At each point x, this is just an ordinary number. Doesn't matter which order you put it in. Numbers times operators are operators times numbers. Right. So just think of psi of x as a collection of numbers, one for each x. Right. So
Complex number.
in general, complex numbers, yeah. Yeah, they will in general be complex numbers. That, of course, depends on the solutions to the Schrodinger equation, whether it's real or complex, but that's right.
Yeah, and I take this to mean that the quantum field description of a particle is you basically do a creation operator on the vacuum space. How would you define a second particle?
By applying, again, another. You want to put a particle in a position y on top of this?
A phi star to the
Yeah.
left of it?
Yeah. If you wanted to put another particle at position y. Okay, let's make a two-particle state. Good. Let's make a two-particle state and one more observation about it. Here's a two-particle state. This is a particle at x and a particle at y. Now, x and y could be the same point, or they could be different points. Right? Let me point one thing out, one interesting fact. The psi's are made out of annihilation operators. There are no creation operators in here at all. Every annihilation operator commutes with every other annihilation operator.
Wait, the side dagger is a creation operator.
No, I'm sorry, did I make a mistake? Yeah. Right. Side dagger is a creation operator, of course. But still, it's true that every creation operator, this is the important thing, it wasn't whether it was creation or annihilation, each one commutes with every other one. Okay? Every operator in here creates, Every operator in here commutes with every operator in here. That means psi dagger of y and psi dagger of x commute. Let's call this the state with a particle at y and x. Well, this is also equal to psi dagger of x times psi of y on O. Dagger. Thank you, I'm losing it. And that's equal to the state with a particle at x and a particle at y. Notice they're equal to each other. They're equal as a consequence of the fact that these commute. All right? The fact that these commute, because they're built out of oscillators in a certain way, tells us that it doesn't matter which order we put which order we write the particles in here. In other words, particle 1 at y, particle 2 at x is the same as particle 1 at x, particle 2 at y. That's the defining property of bosons, that it doesn't matter which order you express them. A particle Harry over here and Jeffrey over here is the same as Jeffrey over here and Harry over there.
So that's fully equivalent to symmetrization?
It's fully equivalent to symmetrization, and it tells you that the particles are most definitely bosons. So I didn't really have to say from the beginning, well, we're going to study bosons. I could have started with this construction, and we would have derived that the particles studied this way are bosons. So the interesting question is, well, how the hell then do you make fermions? Yeah. That's more abstract.
So does this imply that x and y are the same kind of boson?
X and Y? X and Y are positions.
They got x and position.
Yeah. They're the same kind of bosons. That's right. They're the same kind of bosons. Right. So a given quantum field describes one type of particle. There's a quantum field for photons. Well, actually, there are two quantum fields for photons because of the two polarizations. There's a quantum field, let's say a photon's along some axis. There's a quantum field for the photons polarized one way, another quantum field for the photons polarized the other way. There's a quantum field for each different type of particle. There's a separate quantum field. And if you want to make that kind of particle, you apply that quantum field. So that's what a quantum field is, or at least in its simplest incarnation. And I assure you, this is the simplest, but the basic concept or the connection, you see what we're doing is we're talking about the connection between particles and fields. Here is the connection between particles and fields. This is the field. When you apply it to the vacuum, you create a particle.
You define the field to be this.
You define, yes, that's right, we defined it. But once we've defined it, it's an operator. If we add it to its complex conjugate, it's a Hermitian operator. Hermitian operators are observables. All of a sudden, it takes on a life as something that we can measure and do all the things with observables that we do.
So, do all the properties of fields come out of these creation and annihilation operators? Like
Yes, yes. None of this would be interesting if we were talking about a situation where you could not create and annihilate particles. The whole point of this, well, I take let me say a little less strongly. None of this would be interesting if we were only working in a context where there were 37 particles, never 36, never 45, but 37 particles, end of story. We wouldn't do this. If we're interested in studying the whole set of possibilities of any number of particles, then this is a good tool. But even better when we're studying the possibility of the number of particles itself being ambiguous, meaning to say a statistical variable, a quantum mechanical variable. We can study states in which there's a superposition of different numbers of particles. No particle, one particle, two particles, and these have real meaning. An electromagnetic wave, a laser wave is like that. A laser wave is not a definite number of particles. It's a superposition. 1, 2, 3, 0, 1, 2, 3, and good. Okay, now we're finished for tonight.
For more, please visit us at stanford.edu.